Hello, in this video we are continuing our discussion of section 8.2 on series. In this example we're specifically talking about what's called a telescoping series. So it's called telescoping because of the fact that similar to a handheld spyglass sort of telescope, if you're able to compress a lot of the terms of the series. So if you write out a bunch of the terms of the series, a lot of them end up canceling, and then you're left with only a few of the terms in the series. So you're able to use that to figure out whether it converges or not. So one example of a telescoping series is this sum from k equals 1 to infinity of 1 over k times k plus 1. Now we've been asked to show that the series is convergent and find its sum. So we are told that it converges, which means that it's going to have a finite sum, and the sequence of partial sums from this series is going to have a finite value, and that value is the sum. Now, we're going to use the fact that it's telescoping in order to simplify evaluating the limit of the sequence of partial sums, but in order to do that, we need to somehow write it as something that could possibly allow some of the terms to cancel. So we need to write it, or we want it to be written as where we have some quantity minus another quantity. So in other words, we want to take the 1 over k times k plus 1 and rewrite it so that we have two terms, hopefully subtracting each other so that a lot of the terms will end up canceling. So we're going to take a rational function and rewrite it in terms of two simpler fractions. And the way that we do that is by using a partial fraction decomposition. So we have our denominator factored into k and k plus 1, which means that one of our factors will have a k. It is a linear, so we're just going to have an a in the numerator. The other one will have a k plus 1 in the denominator. That's also linear, so we're just going to have b up here. So now the process is to multiply both sides by the k times k plus 1. Cancels out on the left, so we're just left with a 1 there. On the right, we'll have a times k plus 1 plus b times k. Distributing the a and combining like terms, we're going to have a plus b times k plus a, and this equals 1. So this is going to mean that a is equal to 1 and a plus b is equal to 0. So in other words, b is equal to -1. So this means that 1 over k times k plus 1 is equal to a over k 1 over k minus 1 over k plus 1. And I am sorry, I did not take something into account. With how I had written this here, with having a negative there, I would really need a negative here as well, which would make this a negative, that a negative, and that a positive. Now, the net result is the same because b is going to be a positive 1, but we had this negative written out here, okay? So this is written correctly here. I just didn't quite follow the negatives through correctly up here. So 1 over k times k plus 1 is equal to 1 over k minus 1 over k plus 1. So now, in order to figure out if the series converges, which we know it does, but in order to show that it converges, for this to converge, we need to show that the sequence of partial sums converges. Now remember that the sequence of partial sums is obtained by summing a finite number of terms of our series. So the nth term in the sequence of partial sums comes from the sum of our series, k equaling 1, but we're going to stop at n instead of going off to infinity. So we have the sum from k equals 1 to n of 1 over k times k plus 1. So if we use the fact that we have our partial fraction decomposition, this will be the sum from k equals 1 to n of 1 over k minus 1 over k plus 1. And now let's write out our terms. So we're starting at k equals 1. That means we're going to have 1 over 1 minus 1 over 1 plus 1, or 2. Then we'll have plus when k equals 2. So this is k equals 1. Then we'll have k equals 2. We're going to have 1 over 2 minus 1 over 3. Then we're going to have plus when k equals 3. We'll have 1/3 minus 1/4, so on and so forth. We're going to have a bunch of terms in the middle. We don't exactly know how many because we're just going up to a general n. We do need to stop eventually at k equaling n. Before that, we're going to have k equaling n minus 1. Before that, we're going to have k equaling n minus 2, and so on. So we'll just say that the terms in the middle, we're not going to write all of them out. So starting at the end, when k equals n, we're going to have 1 over n minus 1 over n plus 1. When k equals n minus 1, we're going to have 1 over n minus 1 minus 1 over n minus 1 plus 1, so that's 1 over n. When k is n minus 2, we're going to have 1 over n minus 2 minus 1 over n minus 1. And again, middle terms, we'll just say the pattern continues. So this is a telescoping series, which means that a lot of our terms should cancel out. So let's figure out which terms cancel. Notice we have a negative 1/2 and a positive 1/2, so those cancel. We have a negative 1/3 and a positive 1/3. If we were to write out the next term in the middle here, we would get a positive 1/4, so that would cancel out with something in the middle here. Basically, as long as you've gotten 2 terms in a row that cancel with a telescoping series, you can pretty much assume that all the ones in the middle cancel too. Now we need to figure out how much at the end cancels. We have a positive 1 over n and a negative 1 over n, positive 1 over n minus 1 and a negative 1 over n minus 1. So we've got a couple in a row now here. We can assume that this one is going to cancel with something in the middle. So that means that all we're left with is the first term and the last term for this series. I do want to warn you that with telescoping series, you aren't always just left with the first and the last. Sometimes you might be left with the first and the third, and the last and the third from the end, or the first and the third and the fifth, something like that. So you do need to figure it out specifically based on whatever series you are working with. But you should have a lot of terms cancel and all of your terms in the middle, but you need to figure out exactly how many at the beginning and exactly how many at the end cancel. So we are left with 1 minus 1 over n plus 1. So in other words, our sequence of partial sums looks like the sequence of 1 minus 1 over n plus 1, and this is true for n equaling 1 to infinity. So we need to figure out whether this sequence converges or not. With a sequence, the way to determine if it converges or not is to look at the limit as n goes to infinity. So we're going to evaluate the limit as n goes to infinity of 1 minus 1 over n plus 1. And that is pretty easy to see. This first term is a constant, so that's just going to be 1. As n goes to infinity, this second term goes to 0, so we have 1 minus 0, which is equal to 1. So this does mean that our sequence of partial sums converges. Specifically, it converges to 1. So that means that our series, the sum from k equals 1 to infinity of 1 over k times k plus 1, converges, and its sum is 1. In other words, the sum from k equals 1 to infinity of 1 over k times k plus 1 equals 1. So one last thing I want to say here, if I had simply said this at the end, the sum from k equals 1 to infinity of 1 over k plus 1 equals 1, this means that it converges and its sum is 1. So this one statement is exactly the same thing, or that one little thing in mathematical symbols says all of the same thing as this longer statement in English here, okay? So you wouldn't necessarily have to have both of these things in your conclusion here, both of these statements, because they do mean the same thing. Either one is perfectly fine, but they do mean the same thing.